Hey, good morning. So today we will talk about the field of quotients of an integral domain. So that will be the topic of our today's lecture. The field quotients of an integral domain. And before we proceed with the formal construction, let me actually talk about the motivating example. So this is prototypical example. So you're all familiar with the fact that the rational numbers can be constructed using quotients of integer numbers. So this is the construction which appears in school, but let's kind of make a revision of that, which will be beneficial for us to construct precise definitions afterwards. So the elements of Q are precisely the quotients, quotients of the form m over n, or equivalently, we can say that this is the elements n inverse m written. Okay, where this m and n are integer numbers, such that the denominator n is not 0. Okay, so the two quotients are equivalent. So elements of Q are quotients, modular equivalence relation. Which basically tells us that the quotient m1 over n1 is equivalent to the quotient m2 over n2 if and only if the product m1 and 2 equals to the product m2 and 1, right? Okay, so now the question is whether we can generalize this idea, whether we can start with certain ring, right, and look at the quotients of elements of this ring and get another ring. So how we can generalize this idea. For a ring R instead of Z. And before we explain how the generalization work, let's talk about prerequisites. So what do we actually need from the ring R so that this construction have a chance to work? Well, the first thing, because we need something like an inverse, the first thing we have to require is that R must have unity, and that's basically needed to make sense hence for n multiplied by n inverse equals 1, right? Well, the next thing is that R need to be commutative. Have to be commutative. We need it to be commutative precisely because otherwise, if you look at the product of two fractions, let's say n inverse m1 and inverse n1 inverse m1 multiplied by n2 inverse m2 is not necessarily say it's not of the form n inverse m in general. And the last kind of point, which might be non-obvious at this moment, but it will be clear once we will introduce the definition, is that elements in denominator better not be divisors of zero. That's needed for cancellation loss. And one way to ensure kind of the last part is just to require can require R to have no zero divisors at all. Have no zero divisors at all. And that's will surely take care of the last part. So if we combine all these things together, we will get that R should be an integral domain. This literally means that R is an integral domain. And that's precisely the framework we will be working today. So let's go ahead and introduce our first formal definition. So that will be definition 1. So let D be an integral domain. Let D be an integral domain. And first we define the set of formal quotients. The set of formal quotients is precisely the set of pairs of elements from D. D is, so this is the set. This is the set of pairs of elements A, B. Both elements are in D, of course. And of course, we require that B is non-zero. Okay, now the second part of this definition is that we say that the elements, the two formal quotients, let's say Q1 and Q2. Q1, which will be AB, and Q2, which is CD, are equivalent as are equivalent if, exactly as in the previous slide, AD would be equal to BC. Okay, so now the first lemma we're going to prove is that this equivalence introduced in the definition 1 is actually an equivalence relation. So this lemma 1, which basically states that this equivalent, let me introduce notation for that. So let's say Q1 is equivalent to Q2 if, okay, now we prove that this tilde is an equivalence relation. Is an equivalence relation. Okay, so in order to prove that something is an equivalence relation, we need to prove three things: that this tilde is reflexive, symmetric, and transitive. Okay, so let's start doing this one by one. So first, let's say that reflexive. It is reflexive. Okay, so we know that AB equals to AB, right? From here it follows that the quotient Q, which is AB, is related to the quotient Q, which is AB. For all Q in S. Okay, now symmetric. And to be precise, we kind of do AD equals BC, so that should be AB equals BA. Well, it's commutative ring, so it doesn't matter, right? Okay, so now for symmetric. Suppose that quotient 1 is equivalent to the quotient 2, right? Then what do we have? If Q1 is AB and Q2 is CD, this would imply that AD equals to BC, right? Which of course implies that Q2 is related to Q1. And finally, for the transitive part, that's actually the most interesting one here. So let's take Q1, which will be AB. Let's take Q2, which will be CD. And finally, let's take Q3, which will be EF. And let's look at what the equivalence of Q1 and Q2 and Q3 imply. Okay, so from the left part, we get that AD equals to BC. And from the right part, we get that CF equals to DE, right? Now, from both of this part, we will conclude that ADF, actually we need on the left part, ADF equals to BCF, right? BCF. Let's do it this way. So from here we get that ADF equals to the BCF, right? So we just multiplied both sides by F. Okay. So now combining this with the fact that CF equals to DE, we conclude that ADF equals to BDE, right? Well, or if we factor out, that's because R is commutative, we can reorder to move D on the right. So that's AFD equals to BED, right? And now because cancellation laws hold in R, cancellation laws hold in R, this would imply that AF equals to BE. And that's literally the same as Q1 equals to Q3. Q1 is equivalent to Q3. Okay, so that concludes the proof of the lemma. Any questions so far about definition 1 or the following lemma? So this allows us to talk, since the tilde is an equivalence relation, this allows us to talk about equivalence classes. Modulo this relation. So let F be the collection, denote the set of equivalence classes of formal quotients modulo relation tilde. Well, it is common to denote by a kind of semicolon B an equivalence class. An equivalence class. Class of the formal quotient A, B, and S. And we will use this notation. I know the textbook uses slash, and I find this not entirely convenient for the last kind of propositions we will prove today. It's kind of misleading there. So I will use the square brackets and semicolon for an equivalence class of a formal quotient everywhere throughout the lecture. Okay, so now we want to define, our goal is to make, F into a ring. So for this end, we need to define binary operations on equivalence classes, and that's precisely our lemma /definition 2. Okay, it's addition and multiplication in F. Multiplication in F. Okay, so let's look at the two equivalence classes of quotients. B belong to F and C, D belong to F. So define first of all, let's define the product of the two. A over B multiplied by C over D would be defined as the quotient, as the equivalence class of quotients of the following form. And here this is A over B, C over D, right? This is what you would expect. Okay, so now for the addition, we will introduce the addition of quotients by the following formula. C over D as an equivalence class of the following formal quotient, AD plus BC over BD, right? And this would correspond to the standard addition of fractions. Oh, sorry, kind of used the wrong binary operation. Here it is plus. How would you add usually the fractions? The two rational numbers, right? You will bring them to the common denominator and add them. So that's literally what's written on the left. But now we will use this as a definition. Okay. And then the statement, so this was the definition part, and now the lemma part is that operations above are well defined on equivalence classes. Operations above are well defined on equivalence classes. Of quotients. Namely that this kind of, what is the square brackets of A over B? That's an entire equivalence class of quotients, right? Which are equivalent to A over B. And what we need to prove that no matter which representative we take on the left-hand side for the equivalence classes of quotients, we always get the same one and the same result on the right-hand side. So any questions so far before we start with the proof? Okay. For the proof, the first thing to note is that both these operations 1 and 2 define commutative binary operations. Explicitly commutative. Okay, so now suppose that we have two quotients, A1 over B1 and A2 over B2, which are equivalent. And by our definition, this is the same as A1 B2 being equal to A2 B1. A2 B1. I will call this equation star star because I will refer to it later. Okay, so now let's look at the quotient Q1, which is obtained as the multiplication of A1 over B1 by C over D. So this is defined as an equivalence class of A1C over B1D, right? And let's use, instead of A1 B1, A2 B2, which represents the same quotient, and also multiply it by C over D. So what do we get here is A2C over B2D. Okay, so let's look at the following expression. Let's look at A1C multiplied by B2D, and let's subtract B1D multiplied by A2C. Okay, we can definitely factor C and D because R is commutative. So what we'll get is A1 B2 minus A2 B1 multiplied by CD, right? And by the condition star star, this equals to 0. Well, as a corollary, the result of the multiplication Q1 is equivalent to the result of the multiplication to Q2. Okay, so because the operation is commutative, in order to prove that the result of the multiplication doesn't depend on the choice of representative for the second factor, we don't need to do anything, right? It's enough to prove this only for the first factor. So multiplication star from F cross F to F is well defined. Okay, so the same method applies to addition. So again, we take two elements, A1 over B1 and A2 over B2, and we add them with another quotient. Okay, so first let's look at Q3, which is obtained as A1 over B1 plus C over D. Well, by the definition, that's the following expression. That's A1D plus B1C over B1D. And let's look at Q4, which is A2 over B2 added with C over D. And again, our definition of how we add the fractions tells us that this is the same as A2D plus B2C over B2D. So let's look at the difference of A1D plus B1C multiplied by B2D and A2D plus B2C multiplied by B1D. So if this difference is 0, then the quotients Q3 and Q4 are also equivalent to each other. Well, let's factor everything as much as we can. So what do we get here? So for the first For the first part, we get a1 b2 d squared plus b1. Let me move it on the next line actually. So this is equal to a1 b2 d squared plus b1 b2 cd minus a2 b1 d squared and minus b1 b2 cd. Okay, so this cancel immediately. Now for the rest, we can factor d squared and get a1 b2 minus a2 b1 d squared, which by the condition star star equals to 0. So Q3 is actually equivalent to Q4. Okay, so this gives us well-defined binary operation, addition and multiplication, on the equivalence classes of quotients. So basically the next proposition would be that it forms that F together with this binary operation forms a commutative ring. Okay. Proposition 1. F together with the binary operation plus n star is a commutative ring. The proof would go as follows. Well, obviously, from the start, we know that plus and times are commutative. It just explicitly follows from their definition. Now, the thing we really need to prove is that they are associative. And the distributive law holds. This is explicitly my definition. Need to prove by calculation. Now, but this will hold, of course. This will of course hold. I'm not really going into that because this will take some time. Okay. Oh, sorry, kind of forgot to mention the following is that if A over B so first of all, the following fraction 0 over 1 is additive identity. And that if kind of A over B, if A over B is not additive identity, A over B belongs to F, then minus A over b minus a over b is an additive inverse. Additive inverse. And this all parts, of course, is just more or less straightforward calculation, similarly to what we did before. Okay, I'm not going to write this down explicitly. Now, what is more interesting is that let me put one more remark. So we need to prove this bulk calculation, and actually, the only interesting part is the associativity of an operation plus. Associativity of plus. Okay. Now, what is more interesting is the proposition 2. Proposition 2. So let D be an integral domain. And F star be its ring of quotients. Then F is a field. In other words, every non-zero element X in F has multiplicative inverse. And that's, if you remember, what was the main goal of our construction, multiplicative inverse. We wanted to extend our ring to a field. So that was the primary motivation for introducing rational numbers, right? Starting from integers. Okay, and here the proof would basically go as follows. So first of all, this fraction, the equivalence class of fractions, fraction 1 over 1 is multiplicative identity. Again, this part is immediate from the definition. And the second part is that if the fraction a over b is not an additive identity, of f, or in other words, a is non-zero, then the equivalence class of a fraction b over a is the multiplicative inverse. F inverse. And again, this is basically immediate from the way how we defined multiplication of fractions. Okay. So now recall that integer numbers was actually a subset of Q, right? Was embedded. Was a subring of its quotient field of quotients. And this actually generalizes to the following lemma. So let D be an integral domain, and F be its field of quotients, then the following map I from D to F given by I of A equal to A over 1 is an injective ring homomorphism. Is an injective ring homomorphism. Or in other words, the original integral domain D is isomorphic as a ring to a subring of F. Okay. So the proof is more or less straightforward. The fact that it satisfies the homomorphism property. Let me say just a few words. Now this proof. So note that I of A star B. This is A B. Well, I of AB. Let's not use star here. I of AB is the product of two quotients A over 1. Oh, is the quotient AB over 1, which is just the product of two quotients A over 1, B over 1. This I of A, I of B. The injectivity part for the injectivity part assume I of A1 equals to I of A2. And that's really the same as A over A1 over 1 equivalent to A2 over 1. And this is the same as A2 times 1 equal to A1 times 1. Okay, so no different elements are mapped to the same equivalence class. Okay, so let's just summarize everything we have proved to the moment as a theorem 1. So summarizing, we have proved theorem 1, which is formulated as follows. So any integral domain D can be extended to a field. Can be extended to a field. F of quotients of D. Okay, so this moment, kind of, you might ask what we already know that every field is already an integral domain. So what will happen if we take a field and try to extend it to its field of quotients? So that'll be kind of example slash proposition 2. So let D be a field. In particular, D is an integral domain. So we can consider its field of quotients. So we can consider its field of quotients F. And in this case, what you will find out, is that D will be isomorphic to F as rings. In other words, if you have started with a field where every element has multiplicative inverse, you won't extend it any further. Okay, so that essentially concludes the first half of our lecture, which deals with the existence of the field of quotients of an integral domain. So do you have any questions about the material up to this moment? Now it turns out that this extension of an integral domain to the field of quotients is actually unique. Part 2, and that was what will be dealt in part 2 of our lecture. Uniqueness of extension of G to a field. And it turns out that one can actually prove the following theorem. That'll be theorem 2. That if Okay, so let F be the field of quotients of an integral domain D. Field of quotients of an integral domain D. And now let D be any embedding, be any embedding of D in a field L. Field L. So suppose that we have a field L and we have a subring of L, which is an integral domain. So then there exists a ring homomorphism phi from F to L, an injective ring homomorphism. Now, in other words, sorry, that's a bad statement. It's kind of misleading. Sorry about that. And then there is this psi F to L, which gives an isomorphism, of F with a subfield of L, and phi of A equals to A, are all A in D. Okay, so this can be summarized in the following diagram. So suppose we have an integral domain D, right? So as we proved, it injects to the corresponding field of quotients F, right? And at the same time, let's suppose that L is that D is actually a subring of a field L. Then what you will find out is that D is a subring of another field, which is psi of F, which is a subfield of F. And these two are actually isomorphic. Here, all arrows are injective ring homomorphisms. Okay. So how do we prove that? The way we construct this kind of psi is precisely because L is already a field. So every non-zero element has multiplicative inverse there. So proof. Let's first note that L is a field. So there exists a multiplicative inverse for every non-zero element there. Zero, L small, and L. Okay, so then what we can do is we can define function let me start it on the next page. Define function psi from F to L by the following formula. So we will take elements of F are equivalence classes of quotients, and where we will send it to B inverse A. Now, an important part is that inverse and multiplication on the right hand side are in L. Inverse and multiplication are in L. Okay, so we need to prove 3 claims about it. Kind of claim 1 is that psi is well defined on equivalence classes. Psi is well defined on equivalence classes. And indeed, suppose that we have 2 equivalent fractions. Suppose that the equivalence class of A1 over B1 is the same as the equivalence class of A2 over B2, right? So this is the same as A1 B2 equals to A2 B1. This is multiplication in D. In D. Well, because D is a sub-ring of L, this means exactly that A1 B2 equals to A2 B1, where the multiplication is in L. Multiplication in L. Well, but in L we have inverses for all non-zero elements, right? And B1, B2 are non-zero because for the fractions we never allow the second element to be 0, so we can invert them. So we can look at A1, B2, and we need B1 inverse, B2 inverse. Let's multiply both sides by B1 inverse, B2 inverse. Is the same as A1, A2 B1, B1 inverse, B2 inverse. And this is all multiplication in L. multiplication, and inverses are in L. And from here, we conclude that A1 B1 inverse is equal to A2 B2 inverse. And that's precisely would mean that psi of A1 B1 equal to the psi of A2 B2. So this psi is well defined on equivalence classes. No matter which representative of the equivalence class of a fraction we take, we always get the same element of L in the end of the day. Okay, so now there is a second part. Oh, sorry. Now there is a second part, which is claim 2, that psi is injective. Claim 2. Psi is injective. Is injective. Okay, so let's take A1 B1 and A2 over B2, and let's assume that they are such that the psi of the first fraction is the same as the psi of the second fraction. A1 over B1 equals to the psi of A2 over B2. Now, this is just by definition. This is the same as B1 inverse A1 being equivalent to B2 inverse A2, right? And again, let me stress this out, that inverses and multiplication are in L in both of this. Okay, so now we can continue this calculation in L. And we can multiply by B1, B2 on the both sides, the above equation. B1, actually we need only one-way implication. This is still true because this is an integral domain, but B1, B2, B1 inverse A1 is the same as B1, B2, B2 inverse A2, right? Now canceling B1 with B1 inverse on the left and B2 with B2 inverse on the left, we get that B2 A1 equal to B1 A2 in L. But because D is a subring, and here the calculation, kind of A1, B1, A2, B2 are elements of D. Because A1, A2, B1, B2 belong to D, and D is closed under multiplication in L. Well, just say that D is a subring. Subring of L. It would imply that B2A1 equal to B1A2 in D as well. And that's precisely that's precisely a statement that fraction a1 over b1 is equivalent to the fraction a2 over b2. So that's the proof of claim 2. Any questions so far? So kind of the important part is to keep track kind of where the multiplication happens, whether it's in D or in L at this step.
Can
Yes.
we talk about field homomorphisms? Homomorphisms.
Of course, but there's actually only one thing can happen. It's rather simple. You can extend one field by the other. So this is a great question. So we can talk about the field homomorphisms, right? But field homomorphisms are a particular case of a ring homomorphism, right? Just when both both elements are fields on the first place. Is it clear? Because the point is there is only one way to extend inverse. So let me remark on that. Side remark. If phi was a map from F1 to F2, right? Is a ring homomorphism and F1, F2 are fields, then necessarily phi of x inverse equal to phi of x inverse. And in fact, phi must be injective. And that's because if it kind of has kernel, right, then it will never satisfy the ring homomorphism property. And as a corollary, phi of F1, well, as a corollary, F1 will be isomorphic to the image phi of F1, which is just a subfield of F2. So there's only one non-trivial field homomorphism. Is it clear? Anyway, so let's get back to the proof. We can talk about this later. Okay, so the final claim we need to prove this theorem is that our psi is a ring homomorphism. So psi is a ring homomorphism. Okay, so let's see where psi sends the product of two fractions, a1 over b1 and a2 over b2. So, oh, this is psi. Sorry about that. So this is psi applied to a1, a2 over b1, b2. Right, and this is b1 inverse, b2 inverse, a1, a2. which, as you might guess, is the same as B1 inverse A1 multiplied by B2 inverse A2, and this is exactly the same as psi applied to the quotient A1 over B1 multiplied by psi applied to the quotient of A2 over B2. Okay. Now, the same thing goes with kind of the addition of two quotients. So if we add A1 over B1 to A2 over B2, 2 over B2, this is what we get. We get psi over psi applied to the following quotient: A1 B2 plus A2 B1 over B1 B2. That's B1 inverse B2 inverse multiplied by A1 B2 plus A2 B1. And if we expand this out, what we will find is that this is B1 inverse A1 plus B2 inverse A2, which is precisely psi of A1 over B1 plus psi of A2 over B2. Okay, so now summarizing, if we have psi from F to psi of F, it is a ring isomorphism. It is a ring isomorphism. Equivalently, a field isomorphism. Field isomorphism. Right. And that will be the end of theorem 1. Okay, so any questions about this theorem or its proof? So let me just go back to the statement. So in the first part of the lecture, we proved that every integral domain can be extended to a field. And what essentially theorem 2 does, it shows that this extension is essentially unique. So in other words, if this integral domain can be embedded in any other field, then the field of fraction of this integral domain is just a field of L. So that's what we just proved. So in other words, there is no other way to embed integral domain in a field such that we will get kind of the that we will get a subfield generated by elements of D and its inverses any different. Okay, so again, with this theorem, let's discuss the part which is kind of interesting. What happens if we already started with a field? Corollary 1. So let F be a field. Be a field. In particular, its integral domain. It is an integral domain. Then fields of fractions, then f tilde, the field of fractions of f is isomorphic. Of f is isomorphic. Oh, I already talked about this. Sorry, that's isomorphic to f. So if you look at this field, right? So this will be a field of fractions. We know that f injects into a field of fractions, and if we have an embedding of f, right? Then by the theorem 2, what we'll get is that phi of f tilde is isomorphic to f tilde, right? Which is kind of in between f and f. Okay, so for the proof, apply theorem 2 for d equals f and L equals f. Okay, so let's talk about examples. So the boring examples, that will be example 3, probably. That field of quotients, of Q, R, and C are isomorphic to Q, R, and C respectively. Now let's do example 4. Let's look at the ring from one of the homework. So let's say from one of the homework assignments. So let's say that ring R will be the subring of reals, which are numbers of the following form. That's n plus m square root 2. So here m and n are integer numbers. So it is an integral domain. Is a subring of R, hence an integral domain. Now the claim is, if we look at the field of fractions, well, field of quotients, field of quotients of R is isomorphic to the following thing. It's isomorphic to a subring of reals, which consist of elements of the form a plus b squared 2, where a and b are both rational numbers. Now there is kind of a long proof, which I don't really have time for that. So let me just, in the last minute, let me basically mention example. That was example 4. Example 5. Same idea applies to Gaussian integers. Same idea for Gaussian integers. Okay, so if you have kind of Gaussian integers, the rational complex numbers be its field of fractions. Okay, so I will stop here and I will be glad to answer your questions. And of course, I will just save the video from the lecture and continue with office hours in a few minutes. Okay.
So Professor had that.
Yeah, I'll just restart this meeting, so the video will be saved from the lecture, and I will be back in a second.